Now let's put everything we've learned about graphing ellipses and hyperbolas together, including not having the center at the origin. And let's look step by step how we would go about graphing an ellipse equation and a hyperbola equation. First of all, you have to identify what type of figure you have. Okay, so when it's written in the form of an x squared over a number plus a y squared over a number equals 1, and those two numbers are different and it is a plus, not a minus, then it is an ellipse. So that's how you identify. Now the second thing I want to look at is, or the first thing I want to look at in my ellipse is what is the center. So I look at these two numbers here, and this tells me that the center is positive 3, negative 1. Then I look at the two numbers underneath. If the number is underneath the x, it tells me that tells me the number squared. I'm not going to worry about a and b right now, but that tells me if I take the square root of that number, how far I go in the x direction. So in the x direction, I'm going to go plus or minus the square root of 16, which is plus or minus 4. In the y direction, from the center, I'm going to be going plus or minus the square root of 25, which is plus or minus 5. So now this is going to give me an idea of where to draw my axes. Notice there's no x and y axes on here because I want to sort of plan ahead. So let me think here. So if I were to draw an x and y axis, I'm going to be at 1, 2, 3, negative 1 for my center, and then I'm going to be going out 4 and then up 5. So this kind of tells me I better have my y-axis over to the left a little bit more, like maybe around here. And then I want to have my x-axis maybe slightly above the center, just maybe right here. So there's my x-axis. And this will allow me to have plenty of room then to draw it without running out of space. So the first thing I'm going to do is plot my center point. There's my center, and you know I'm not going to call it C because that might get confused with the focus. There's my center point. Then I'm going to go out 3 in the, I'm sorry, not 3, out 4 in the x direction and 5 in the y direction. So out 4, 1, 2, 3, 4, 1, 2, 3, 4, up 1, 2, 3, 4, 5, down 1, 2, 3, 4, 5. So there is the framework so far for my vertices. Now I'm not going to actually draw this yet because I want to incorporate those latus rectum endpoints that I talked about in the other video, so I can get another 8 points or another 4 points to figure out how wide it is kind of here and here. So I'm going to find the focus next. So the focus is the distance from the center of the focus, C, is the square root of 25 minus 16, which is the square root of 9, so plus or minus 3. Now how do I know that I'm how do I know where to put that plus or minus 3? It always goes on the longer axis. I also know that I'm subtracting here because if I'm adding, that would make my distance to my focus bigger than the distance to the vertex, which is not what I want because I need to have the focus inside the ellipse. So I have to put it on the longer of the two axes, which is in the y direction. So I'm going to go up 3 and down 3 for the focus. Now what I want to know then is if I were to go to the right or to the left, and I'm going to erase these arrows in just a minute, but if I'm going to the right or to the left, how far to the right or left do I go to find another point that's on the ellipse? That's what the latus rectum endpoints tell me. That is the b squared over a. So if I'm going to go plus or minus b squared over a from the focus to find 2 more points. Now here's where it's important to know which one is B and which one is A. A is always the radius that has the focus on it, is the longer one in the ellipse. So A is equal to the square root of 25, which is 5, and then B squared is the 16 here. So 16 divided by 5 is going to be 3.2, 3 1/5, which is 3.2. So what that tells me is I'm going to go over 1, 2, 3, 3.2 is going to give me, so I'm going to go ahead and say that, kind of label this. 3.2 units is going to give me another point on the ellipse right here. And then if I go 3.2 the other to the other side. Looks like I erased part of my y-axis here. Let me put that back in. 3.2 this way, that's another point on the ellipse. So this little dotted line here is called the latus rectum. It is the chord that connects two sides of the ellipse. So I'm going to go 3.2 down and on the bottom side as well. And what this does then is gives me 8 points now for drawing my ellipse. So when I draw my ellipse, it's a lot easier to draw because I have more values, kind of to help me figure out how round it is. I'm going to try that one again. So notice that is a fairly round looking ellipse. I might have made it, I probably would have drawn it much too thin if I hadn't had those extra points to help me. So thinking of thinness, remember we talked about eccentricity measures how round an ellipse is. So let's calculate the eccentricity. So E is C over A. C in this case is 3, A is 5, so it's 0.6. That's smaller than the example that we saw before, which is 8. So this is a little more round than the one that was 0.8. Now let's look at the hyperbola. And I already told you it was a hyperbola, but the way we would recognize it's a hyperbola is that these two squared terms are subtracted instead of added. So this is the hyperbola. We notice the negative sign, or the subtraction. You'll notice that other than that subtraction sign, everything else about this equation is exactly the same as it was for an ellipse. And I did that deliberately because I wanted you to see the connection between the two. So the center of the ellipse is still 3, -1. If I want to go in the x direction, I'm going to be going plus or minus the square root of 16 or plus or minus 4 because that is the number under the x term. The number under the y term is 25, so I'll be going plus or minus 5 in the y direction. But instead of using that to draw an ellipse now I'm going to draw the box. This is what determines the box where the asymptotes go. So I'm going to go ahead and do my y-axis. Let me see where I put it. I'm going to put my y-axis and my x-axis about the same place that I did before because that worked really well. So there's my y-axis, and I don't know how exactly where my x-axis was, but yeah, let's just put it like this. That'll do. Okay, so I have 3, 1 as my center. I'm going to go 4 in the x direction, and I'm just going to make kind of a little mark to show that's where one side of my box is going to be. And then I'm going to go 5 up and down. 3, 4, 5. That's going to be the upper side of my box and the lower side. So my box is going to be kind of like this. Not just kind of like, this is going to be my box. So here's my box. Now, once we have the box, we're going to draw the asymptotes. Remember, the asymptotes will go from the corner of the box to the center to the opposite corner. So, you know, kind of through this way, and then the other asymptote will go through this way. So I would suggest using a ruler to help you and drawing in those two asymptotes and extend them as far as you can on the graph. So I'm going to go ahead, I've actually got a little paper ruler that I'm doing this with to try to make mine as straight as possible. And I'm still using the dotted lines because this is not exactly the, well actually I'm not going to put the arrow is not all that important for this. I think I'll erase that little arrow. So I'm just going to extend that as far as I can and then do the same thing the other direction, because remember these cross lines serve as a framework, kind of a scaffolding to put the hyperbola on. It's how I know how wide to make my hyperbola. Okay, so there's, kind of extend that down a little bit. There we go. Now, one thing we didn't talk about yet is which direction does this open? It opens in the x direction because the x direction is the positive term. Okay, that's the positive term, is the x term. So that means it's going to be opening side to side. Now, that means the two vertices are right here and here, and the transverse axis that connects the vertices is this axis here. So when I know which direction it opens, that tells me which way A is. This distance from the center to the vertex is A. So A equals 4. The distance from the center to the top of the box then is B, so B equals 5. And that's going to be helpful now when we are doing our B squared over A to get those extra points. All right, now focus. Remember, in the hyperbola, the focus is longer than that major axis, that half of that transverse axis. It's out here and out here. It's going to be to the side. So I have to add the A squared and the B squared to find C. So I'm doing 16 plus 25, which is the square root of 41, which turns out to be approximately 6.4. So remember, I'm going to go from the center. I'm going to count 6.4 units in either direction, in the x direction. Okay, so I'm going to go 1, 2, 3, 4, 5, 6.4. Remember, I'm counting from the center and not from the vertex. 1, 2, 3, 4, 5, 6.4, so about out here. Okay, so there's my two foci. Now, it turns out there is another lattice rectum length, and I'm just going to kind of dot this in to show you. There's a chord that's going to connect the two sides of the hyperbola, and I can figure out how long that chord is by doing B squared over A. So B squared over A in this case is going to be 5 squared over 4. So 25/4 or 6.25. So what that tells me is I'm going to count from the focus up and down 6.5 units. So if I count up 1, 2, 3, 4, 5, 6, 6.25 is about right here. Actually, I make this red so it's really obvious. Okay, and then 1, 2, 3, 4, 5, 6.25 is down here. I actually drew that the right length without even realizing I had done it. So what that does is help me now when I draw my hyperbola, I have a little bit better idea of how to curve it. Now notice what I'm doing here is as it goes out, it has to get closer to the asymptote. So you do not want to draw it so it looks like that, okay? Because that is not getting closer to the asymptote. That is getting farther away from the asymptote. So you want to have it go through these points and then be closer. So this distance, remember, was the B squared over A, which was 6.25. That's really hard to read. I think I will erase that and try again. Let's put it in black. So B squared over A, which is 6.25. Okay, that's that distance here. And then you have the same thing going the opposite direction down here. Okay, then if I do that on the other side, here's my other focus. So I'm going to count up 1, 2, 3, 4, 5, 6.25, sorry. 1, 2, 3, 4, 5, 6.25. So now I can do the same thing on the other side. And notice at the end I'm making my arrows get closer to the asymptotes, not farther away. So those extra points, that B squared over A point, gives me a couple extra points that I can use then to help get a better shape. I didn't realize I'd drawn half of my hyperbola red and half of it blue. So you know what, I think I'm going to make it all blue just to make it look a little bit better. So let me change that color to blue. There we go. So now we have it blue on both sides. So that's how you use the lattice rectum endpoints to help shape your hyperbola. Now last thing is let's calculate the eccentricity. So E is C over A. C in this case is 6.4 and A is 4. So 6.4 over 4, actually that 64 divided by 4 is 16, I believe. I think that's right. 16, yeah. So this would just be 1.6. So we can see that's greater than 1. That's a characteristic of the eccentricity of a hyperbola.